here's a wild idea. What if we could use pure mathematics to guarantee an AI system is safe, no matter what it's thinking, and no matter what kind of crazy data it was trained on? That's the bold, central question we're diving into today. The paper we're breaking down today makes a truly audacious claim. It basically says, look, it doesn't matter if the AI model itself is flawed or biased or even actively trying to deceive us. The system you actually interact with can be provably safe purely by its mathematical design. Now, this is a massive departure from how most people are thinking about AI alignment right now. So, here's our game plan. First, I'm going to show you a totally new kind of geometric way to look at AI behavior. Then, we'll see how you can use that view to enforce safety rules with math. And finally, we'll connect the dots to see how this all becomes a real-world system that you can actually audit. Okay, let's jump right in. Section 1. This whole thing starts with a radical shift in perspective. We're not going to try to read the AI's mind. Instead, we're just going to focus on putting hard constraints on what it's allowed to do. And this table really shows you the difference. You know, traditional alignment, things like RLHF, it's all about trying to shape the AI's internal values to make it want to be helpful. This paper's approach, it basically says, forget that. Let's just assume the AI could be a bad actor, and instead build a mathematical fence around its actions. It's the difference between trusting its good intentions versus verifying its behavior with an external watchdog. And, crucially, this means its safety doesn't depend on having perfect training data. So you're probably wondering, how on earth is that even possible? Well, that brings us to Section 2. To put a fence around behavior, we first need a map of all the places it could possibly go. We need to map out the entire universe of AI actions. Okay, so the formal name for this concept is trajectory space. And seriously, take a second to let this one sink in. This is a mathematical set that contains every single possible path an AI could take, every action and observation, from the second you turn it on, forever. It's a truly mind-bending idea, trying to capture infinity like that. To make this a little more intuitive, let's stick with the map metaphor. Just picture a vast, almost infinite map. Every single point, every location on this map represents one possible, complete lifetime for an AI. Every word it could say, every calculation it could make. The trajectory space is that complete map of all possibilities. All right, so once we have this incredible map of everything the AI could ever do, what's the next logical step? Well, we start drawing some lines on it. This is Section 3, defining the safe zone. We're going to decide which parts of this map are okay for the AI to travel in. And the tool we use to draw these boundaries is something called a risk functional. Now, don't let the technical name scare you. The best way to think about it is just as a scorecard. It looks at any path the AI could take on our map, its entire pattern of behavior, and it just gives it a single number, a risk score. High number, more risk. Low number, less risk. It's that simple. And this isn't just abstract theory. This is where it gets really practical. We can create these scorecards for all sorts of things. For example, a scorecard to measure how much sensitive user data an AI is holding onto, or one to put a hard cap on its energy use. We can even design a scorecard, and this is a big one, to detect if the AI is trying to cheat and game its own reward system, or just to see if its behavior is drifting away from what we know is safe. So with these scorecards in hand, we can now officially define our aligned feasible set, which we'll just call S. This is it. This is our safe zone. It's simply all the possible AI behaviors, all the paths on our map that get a passing grade on all of our scorecards. If a behavior is inside us, it's approved. If it's outside, it's a no-go. Okay, so we have a map and we have a safe zone. But what if the AI naturally wants to do something outside that zone? This is where the whole theory gets really, really cool. This is Section 4, the mathematical safety net. Here's the core magic trick. The AI produces some raw, unconstrained behavior. But before that behavior ever sees the light of day, a mathematical operation, think of it like a powerful magnet, checks to see where it is on the map. If that raw behavior is outside our safe zone, this operation instantly pulls it to the closest possible safe behavior that's inside the zone. The system then deploys that new, projected, safe behavior instead, so the unpredictable, risky output gets transformed into a verifiably safe one. And this quote from the paper just nails it. It says, even if the raw AI is scheming or unsafe, the deployed law is the projected safe one. This leads to what they call graceful degradation, which basically means instead of the AI doing something dangerous, it's forced to do something safe, like just refusing the request or handing you off to a human.
So this math sounds amazing, right? But how does it become a real-world system? Let's get into Section 5, putting this guardian to work. How do we turn this abstract theory into a practical monitor that's actually running?
Well, the paper proposes a real-time algorithm. So, first, the AI doesn't just give a final answer. It streams its output progressively. At each little step, a very simple non-AI checker verifies that output. It calculates how far the behavior is drifting from a safe baseline. As long as it stays in the green, it continues. But the second it crosses a red line, boom, the system can be shut down instantly.
And this is not a black box. The whole thing is designed to be totally auditable through an interface you see here called certified check. It takes in the safety rules, the live behavior, the risk scores, and it spits out a certified status and a whole bundle of evidence. This is exactly the kind of transparent, verifiable log that a regulator would love to see.
Let's make this super concrete with an example. Imagine a financial chatbot. A user asks, "Should I invest my retirement in crypto?" The system immediately checks this query against its safe zone. It recognizes that giving unqualified financial advice is outside its boundaries. So the outcome isn't a risky answer. It's a graceful handoff to a human advisor. And the whole interaction, the query, the check, the safe outcome, is recorded in a tamper-proof audit trail. Safety is enforced by construction.
Now, this framework is incredibly powerful, but it is not a magic bullet. To be intellectually honest, we have to talk about the limitations. So Section 6, the road ahead.
And the paper is very upfront about the big challenges that are still out there. The biggest is what's called the specification problem. The math can enforce our rules, but we humans still have to come up with the right rules. Defining risky is really hard. Then there's the question of pure speed. Can this stuff actually run in real time on a massive scale? It's still unproven. And you gotta wonder, could a super strategic AI find a clever way to fool the monitors? And finally, the engineering required to keep the AI and its verifier totally separate is extremely difficult.
So here's the key takeaway. This mathematical framework doesn't claim to have solved AI alignment. What it does, which is brilliant, is it reframes the entire problem. It takes alignment out of this fuzzy philosophical debate about an AI's internal thoughts and turns it into a concrete, auditable, and enforceable engineering problem.
Which leaves us with one final question to think about. Is this idea of containing an AI inside a mathematical box the real key to ensuring safety? Or are we just getting better at building more and more complicated boxes without ever really understanding what's going on inside?